Hello, regular statisticians. We are going to finish Chapter 8 on hypothesis testing. So here we go. So we got through 4, 5, and 10. We finished that. So now we're on to a p-value. So here's the definition. That is a long definition. So obviously you can pause to finish getting caught up in any of this stuff, but it's a probability that you would find your answer, or more extreme than that, assuming the parameter was true. This will make much more sense when we start getting into an example. So let's hold off on trying to overly understand this currently. Level of significance. So the significance level, let's see here. If the p-value is less than alpha, alpha is your significance level, then we reject the hoe, which implies we have convincing So if the p-value is going to be greater than alpha, or really it's greater than or equal to, but then we fail to reject the hoe, implying we don't have convincing evidence for So this is that old rhyme: when the p is low, reject the hoe. And then obviously if p is greater than that, we keep the hoe, but you can't say keep instead. You gotta say fail to reject. Any questions? Any questions? Bree? Nope. Okay. So let's move on. Determine whether to reject the hoe based on the p-value. If the p is less than, let's just say less than alpha, we reject HO. So here's the p-value, here's alpha. So it's 0.45 less than 0.05. No. So do we reject HO? No. Because this one, see, this says p is greater than alpha. So we're basically keeping HO. Are we supporting HA? Well, if I'm not getting rid of the hoe, I can't choose the Haas, so no. Because you either are, you've got to take one of them. So if I'm keeping the hoe, I'm not supporting the Ha. So the P is low, reject the hoe. And if I am rejecting the hoe, I am supporting the ha. So do we support the ha? Yes. Now on this one, 0.06 is less than 0.10. So P is low. Reject the hoe. And if I'm getting rid of the hoe, I'm going to be supporting the ha. And so forth and so on. So the smaller the P, the more evidence you have to support the ha. That's how it works. So the level of significance is really the cutoff probability. So in the other chapters, we were always saying anything under 5% was unusual. Well, now I can set it wherever I want. So this is 5%. So anything under this is unusual. But now I'm saying 1%. So now this is unusual. Anything under 1%, 10%, 20, half. All right, 14. Original claim, fewer than 20% of M&M candies are green. All right, the hypothesis test results in a p-value of this. Assume a significance level of that. All right, state a conclusion about the null. So what we're going to do is we're going to state the HO and the HA. Fewer than 20 are green. It's a proportion. Fewer than 20. So the other one is going to be this. Remember, the hoe gets the equality. And are we going to reject HO or fail to reject HO? All right, the p-value is this. Alpha is that. Is the p lower than that? No. So since P is greater than alpha, we fail to reject HO. So if I'm failing to reject this, that really means I'm keeping it, but you can't say that. State a final conclusion. So we talked about the hoe, and now we got to go on to the ha. So if I'm failing to reject this, I don't have evidence to support that. We don't have convincing. To support the fact that the proportion of green is less than 20%. Let's try 15. Original claim, women have heights with a standard deviation equal to 5 centimeters. Well, if it's equal to standard deviation, so this one's going to be not equal to. That's our p-value. That's our alpha. Is p less than alpha? Yes. Since p is less than alpha, we reject HO. So if I'm rejecting HO, I'm supporting that one. So we do have convincing evidence to support ha. It doesn't mean ha is true, it just means I have evidence to say it's true. Because you never really know unless if you measured all women. It would be pretty hard to do because you could have some cat lady that's not coming out of her house, a homeless woman, a woman that's not answering her phone, all sorts of possibilities. Okay, 16. For each question below, assume the significance levels, that's alpha, is 0.05, and use a given statement to find the p-value and the critical values. Okay, so here's our test step. So you draw a curve. These are z-scores, so that's 0. Here's -2. Okay, so testing the claim. So this is going to be the ha, and it's facing left, so that's a left tail. So I got to find the area under the curve from here to here. So that's norm CDF, -99, -2, 0, 1. And I wish I could do this in my head. That would be awesome. Let me get this. That is a p-value. it's the area under the curve in the direction of Ha based on what you found. So find the p-value and find the critical values. All right, so the critical value is this. All right, if the significance level is 0.05 and it's on the left side, right here, so the critical value. So what that's saying, alpha is 0.05, so that's going to be inverse norm, 0.05, 0, 1. Z critical value or Z star is going to be negative 1.6, I don't know, 4 or 5. So notice I have a test stat and I have a critical value. Sorry. Is my test stat in the critical region? See, if that's negative 1.6, my test stat negative 2 would be over here. So my test stat is in the critical region, that means reject HO. My p-value is less than my alpha, that means reject HO. So there's two ways of rejecting it. You either compare your p value to alpha, or you compare your test stat to your critical value, which we did, you know, before the Corona break / 2020 / apocalypse. All right, now this one, the test stat is 1.5, and we're testing the claim that it's not equal to, so that's the Ha. So my test stat is 1.5. So what we have to do here, whenever it's a not equal to, we have to double the p-value. So the p-value is going to be the area under the curve. So I just got to do 2 times norm CDF, 1.59901. So you do norm CDF, see, 2 times it. And I get this, 0.13. That's the p-value. So if I have to find a critical value, probably should have left more room here. So the critical value, all right, alpha's 0.05, but it's a 2-tail. This is a 2-tail. So I have to split it. It's going to be 0.025. 0.025. So I'm going to do inverse norm, 0.02501. And the critical value is, well, in this case, plus or minus 1.96. So 1.96 is my test stat in the critical region. No, 1.5 is over here, so it's not in the critical region. So I fail to reject HO. My p-value is greater than my alpha, so I fail to reject HO. Type 1, Type 2, and power of a test. Here's the story. Let's say I reject HO, but HO is really true. You know, let's say I'm doing some sort of test where I think the mean weight is, I don't know, for men is 150, and somebody says, well, it's not 150. This is of no importance in life, but let's say I reject HO, but I really should have kept it. Well, that's an incorrect conclusion. So when this happens, that's an error. It's actually called type 1 error. And the probability of a type 1, that's the probability of rejecting HO given HO is true. It's a conditional probability. And that probability is alpha. So if alpha is 0.05, that means I have a 5% chance of rejecting when I shouldn't. Rejecting HO when HO is false. This is a good conclusion. If HO is false, I want to reject it. HA is true. That's also the same thing. This is called the power of a test. If I am keeping HO and HO is true, this is a good conclusion. If I'm keeping HO and HO is false, I don't want to keep a false HO. This is a type 2 error. This is called beta. So it's the probability of keeping HO given HO is false. It turns out that power is 1 minus beta. Beta and power add to 1. This box got screwed. There's no name for it. They're just like, yeah, good job. We don't know who you are. Nice. Now let's put these into action. All right. Even when companies wash chicken carcasses after slaughter, the USDA has found that the bacteria on a quarter of all cut up chicken parts heading for the supermarket shelves, all right, has found bacteria. Okay. It's a good reason to handle raw chicken carefully, wash your hands afterward, a lot of hand washing, and cook the meat well. Under the USDA's new standard, companies will be required to reduce the frequency of contaminated chicken parts to 15% or less. A meat inspector reports that the chicken produced by a company exceeds the USDA limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. Use 15% as P. All right, this is actually true. All right, you can Google this. So there's the HO, there's the HA. So a type 1 error would be rejecting HO when HO is true. So if I reject HO, I'm saying I'm gonna, so really that would be that I'm concluding P is greater than 0.15 when it's actually less than or equal to 0.15. It's wrong because it's true. So a consequence would be I'm telling people that there's a lot of bacteria on the chicken, but the chicken's actually okay. So a consequence is just wasted product. You're overly nervous, very nervous with this product. A type 2 error would be, you're not supposed to say keeping, but I'm just going to keep saying it. Keeping. HO when HO is false. So I'm keeping HO, so I'm keeping less than or equal to when HO is false, or you could say HA is true. So I'm concluding P is less than or equal to 0.15 when it's actually greater than 0.15. All right, this is brutal because I'm saying it's safe when it's not. So a consequence would be, people could get sick or die. All right, but hey, I saved the company some money, right? Describe the power of the test. The power is the ability. So if you go back to your chart, the power is the ability to reject HO when HO is false. That's a good thing. So it's the ability to, I'm going to word it a little bit differently, detect when P is greater than 0.15 when it actually is. greater than 0.15. Which error is worse? Well, the 2. All right. How can you reduce this error? Well, you reduce 2 by raising alpha. Now, reducing the errors, I want to go back and talk about that before we finish. So, let's keeping n fixed. That's our sample size. Note that too. All right, so if I increase alpha, like from 0.05 to 0.10, I'm going to decrease beta, and power is going to increase. Someone's having a good time up there. These are inverted. You can never be perfect. You're going to make an error somewhere. So if you raise alpha, if you increase the chance of making a type 1 error, you're decreasing the chance of a type 2 error, and vice versa. To decrease both errors and also increase power, you should raise n. Because you're interviewing more people. If your sample size equals your population size, then your chance of making a type 1 is 0 because you tested everybody. Your type 2 is 0, and your power, well, you have a 100% chance of getting the right answer because your sample size is your population. Okay, we will stop there.